As we mentioned before, just like there's an electric flux, we could define a magnetic flux the same way. We have here phi m is the integral of B dot dA. And we could go with the same model as before. The B field is a river. Net you put in it has some area A. The angle between the river's flow and the net's normal vector is the theta, the dot product part. And our chance of catching a fish is like the flux. If B is larger, that's like the river being faster. If the area is larger, that's like the net being larger. And then how you hold it tells you what you're going to get for the dot product. Just like we use the electric flux in Gauss's law, we could define a Gauss's law for magnetic flux. The problem is we wouldn't get any use out of it, because with the electric flux, when we did that, we saw that the electric flux through a closed surface depended on the net charge inside it. But we know that we'll always get zero for the net magnetic charge, because we can't come up with a surface that will enclose a different number of north poles than south poles. So we could write down Gauss's law for magnetic fields, but it won't help us solve any problems in this course. There actually is something that we can use magnetic flux for, though, and that's to explain what was originally a very weird result. We can take a galvanometer, which we can think of as just a really sensitive ammeter, and connect it to a few turns of wire, and when we do that, of course, we get nothing. We get no current because it's just a few turns of wire connected to this thing. However, we notice that if we push a magnet through the wire loop, we get a current. Now, as soon as the magnet stops moving, the current disappears. If we pull the magnet out of the loop, we get a current in the other direction, and again, once it stops moving, the current disappears. So the galvanometer only reads something other than zero if the magnet is moving. Now, we can also hold the magnet still and move the wire around it, and we get the same effects. There we can explain this using our F equals QV cross B, because the electrons in the wire are moving through this magnetic field, so they get pushed around the circuit, and that gives us a current. The thing we don't have, or at least they didn't have in the 1800s, is an explanation for why this should happen if the magnet is moving, because then the charges in the wire are at rest and they shouldn't respond to a magnetic field. So Faraday figured this out, but 50 years or so later, Einstein actually used the fact that you get the same result whether the wire moves or the magnet moves as part of his basis for figuring out that motion was all relative. There's no such thing as absolute velocity, and this is in his theory of relativity. Now, Faraday's law, which is Faraday's law of induction, this is reasonably simple to write down. It says we get an EMF epsilon from a changing magnetic flux phi m through n loops from this simple formula. It's negative n times d phi dt. The fact that there's a negative there is known as Lenz's law, so this is one way to get your name in the physics books, just with this minus sign. What this tells us is the circuit is going to produce an EMF that gives a current that generates a magnetic field that tries to counteract the change. Now, the unit of magnetic flux is the Tesla meter squared, or the Weber. We can do an example problem that's in practically every intro physics book. Let's say we have two parallel conducting rails and we connect a light bulb, which is just a resistor here, in between them. And then we have this sliding conductor, this bar that can move along the other two rails. We have this set up with a magnetic field into the page, and what we notice is if we pull this bar backwards, the resistor will start to heat up, or the light bulb will light up. What's happening is, as we move the bar back, the area through which the field flows is changing. So we're increasing the in the page flux. So the x's mean in the page. As we back this out, we have a larger number of x's going through the area of interest, so we're increasing the in the page flux. The circuit wants to fight that, and the only way to fight that is to produce out of the page flux. If you use the right hand rule and point your thumb out of the screen, that shows that your fingers curl this way, counterclockwise around the circuit. So this is the EMF that's going to be set up, and the current is going to be driven around the circuit counterclockwise, like this. Now, how big is this EMF that's developed by pulling this bar backwards? We can use the formula. We know here n equals 1. We only have one loop of this. If we say the distance between the rails here is L and the left-right extent of this loop is X, we can ignore the negative sign now because we've already figured out the direction. It's, in my opinion, easier to figure this out with physics than math, and we just ignore the negative now because we already know what's going on. So our d phi dt becomes d BA dt, really BA cosine theta, but the angle between B and A never changes. It's always 0, so that cosine theta is 1. We can write the area as L times X, so we've got d dt of BLX. L is constant, the rails aren't moving closer together or anything. B is constant, X is the only thing that changes. So we can write this as BL dx dt or BLV. Don't forget this V is velocity of the bar, it's not a voltage. If we're looking for the current, we get that from Ohm's law, which is this EMF divided by R, or BLV divided by R. What's the power generated in this resistor? The ability to heat water, for example. We can use P equals IV, which means we can just multiply those two together. Here the V is voltage. We get BL velocity squared, the whole thing squared, over R. Now, why do we need that negative sign in the first place? Why do we have to figure out that it's opposing the change? The reason is our induced current, which moves counterclockwise, goes up through this sliding bar. Now, what's the force on an upward current in a magnetic field that goes into the screen? Again, we use the right-hand rule. Put your fingers up the page and then curl them into the screen and you get a force to the left. If the current went the other way, the force would go the other way, and once we bump the bar to the right, it would just start accelerating faster and faster to the right, and that would violate conservation of energy. Now, if we move the bar back to this should be left, we're cutting out some of the flux into the screen. So the circuit will try and give us more in the screen flux. This means we need a clockwise current. Now if we have a clockwise current, that means it's moving down through the sliding bar and the force on it is to the right. The force always opposes the motion. How large is this force? Well, we know the force on a current in a magnetic field from previous work is ILB sine theta. Theta is always 90 here, so we just have ILB. This is our I. This is L and B, so we can write this as BL squared V over R. Now, what's the power required to keep the bar moving against this force? Remember from last semester, we have this mechanics issue. Power is force dotted into velocity. When I write it where this is our force, we dot that into velocity, we get BLV squared over R. This should look familiar because it's exactly the power we found for lighting up the light bulb or heating the resistor or whatever. We have to conserve energy. Now, another example you see in every intro book. Let's imagine we have a coil of N turns of wire, area A, rotating in a magnetic field, so it's going around and around like this. We're going to want to set up a way for the wires coming off of the, we should have two wires coming off of this coil. We got to have some way to tap into them and measure them without the wire being a complete twisted mess in 5 seconds. So we can go back to the setup of commutators and brushes that we had when we introduced the motor. This way we can let our loop turn in the magnetic field and nothing is winding up. But what we have here, we notice this motor, its purpose is to take electric energy and turn it into mechanical energy. A generator is the exact same thing, working backwards. It turns mechanical energy into electrical energy. If we spin this coil, we can do it by hand or steam power or a horse or whatever, but however we spin this, we can charge the battery. Now, the EMF that this rotating coil produces, we still have Faraday's law. It's N d phi dt. We can look at these pieces. The magnetic field is not changing. The area is not changing. What actually is changing? It's just the cosine theta part. So this angle between B and A is all that's changing. So we write it like this. That doesn't look too bad. If the coil is rotating at a constant angular velocity, omega, we know from last semester's angular mechanics that position at any time t is given by theta t is theta I plus omega t. We can assume we start at theta equals 0 just to make life easy. And now we have that the EMF is negative NBA ddt of cosine omega t. This is not a hard calculus problem. We get NBA sine omega t and ddt of omega t, which is just omega. So our final answer, E equals NBA omega sine omega t. What would this look like if we wanted to graph it? What we need here is a fast recording voltmeter, and it's actually called an oscilloscope. If we connect the oscilloscope leads to the ends of a battery, we get this very dull picture, 1.5 volts for, say, a D battery. This is a perfectly flat line. It never changes except over very long times when the battery starts to die. This Y position is the battery voltage. What would it look like if we connected it to the spinning coil's leads? We get this instead. Here we have this sinusoidal curve, and that tells us that the two wires, one of them is at higher potential than the other, and then it's at lower potential than the other, and it just goes back and forth. So this is one complete turn of the coils. We would see this if we plug the oscilloscope's leads into the wall. Now you actually have to be a little bit careful doing this because of the way the oscilloscope is set up, so don't try this on your own. But if you did this and got the voltage reading, what you would find is for a regular wall outlet, we'd go up to 170 volts and down to minus 170 volts. If you did this for your dryer or stove outlet, it would go back and forth between 340 volts, positive and negative.